we will start. Okay. Okay. Mama, Windows 7. Okay. We will start. Okay. So we are still studying transmission line. Okay. Transmission line. Okay. So up to now we have studied that if we have a transmission line like this, okay, this is a transmission line. I just draw the line. Okay. So the wave is propagating through this line. Okay. And the ground plane is already there. Okay. I haven't drawn the ground part. Okay. I just draw the line part. Okay. So here the wave is propagating. Okay. Here the wave is propagating in this direction. Okay. So normally wave propagation direction is normally considered in Z direction. Okay. Okay. So Z direction is the wave propagation direction. Okay. That is the general consideration. Okay. Generally, the wave propagation direction is considered to be Z direction. Okay. So if this point is Z is 0, okay. So this is plus Z and this will be minus Z. Okay. And we have learned that, okay, if a signal is propagating in this direction, the signal also will be reflected. Okay. So there are two waves. Okay. Forwarding wave and reflecting wave. Okay. So total, for example, if we consider the voltage, okay. So total voltage at any general Z point, okay, can be written as VZ. Okay. So let's assume that at Z is 0, the forward voltage is V0 plus and the backward voltage is V0 minus. Okay. And also forward current is I0 plus this direction. Backward current is I0 minus this direction. Okay. So VZ is considered as, okay, V0 plus e to the power minus j beta Z plus V0 minus e to the power plus j beta Z. And also IZ we have considered that I0 plus e to the power minus j beta minus I0 minus e to the power minus jb, sorry, plus jb. We have learned these two equations. Okay. So you need to understand this equation. Let's say that equation 1 and equation 2. Okay. Then again we have learned that. Okay. So let's say that this transmission line is connected to a load. Okay. This transmission line is here connected to a load. Okay. And the load should be connected to the ground. Okay. So this is the load. Okay. So this load may be another uh, transmission line. Okay. Okay. This load can be another transmission line. For example, okay, you have one transmission line. Okay. Then due to several reasons, you have to connect to it another transmission line. That transmission line may be wider or maybe narrower than the first one. Okay. So if you consider this transmission line is the load of this one. Okay. So it can be another transmission line. This load can be another transmission line. Okay. Load refer. It can be another transmission line, another TX line, or maybe this load may be amplifier. Okay. For example, I told you that, okay, in our phone, we use minus I to derive. I couldn't understand. Okay, okay, I will upload. Okay. We use, I can't understand the question, but we use here. I have done any mistake. What's this mean? I couldn't understand. Minus e to the power minus j beta z, no? Yeah, L. Okay. Distance. Okay. Z is the distance. Okay. Distance from 0. Okay. You can, so, yeah. Previously, I think I have put L, no? Here. Maybe. Okay. So you can put L, no problem. Okay. I just, the Z is the length from 0 to here. So you can write it as L, no problem. Okay. And so this load can be another transmission line, or it can be amplified, as I told you that antenna receive the RF signal, then the antenna should be connected to the amplifier, power amplifier. Okay. So antenna and power amplifier is connected through a transmission line, TX line. Okay. So to this TX line, this amplifier is the load. Okay. Then this power amplifier may be connected to the. So if you can, so that amplifier and filter is also connected to the transmission line, this one. Okay. So this transmission line, if you consider this transmission line, the load of this transmission line will be the filter. Okay. So this load can be anything. It is not a resistor. Okay. It is not just a resistor. It can be a resistor. සාමාන්‍යයෙන් අපි load කියන resistor එකට normally. But here no load require the other component. Other actually a filter, it has a referred as impedance. Okay, input impedance. This okay. Okay. So if you connect to a load, okay, if you connect to a load, okay, we have learned that the power is going through, for example, if you consider the voltage, there is a voltage towards the load, and also there okay. Okay. Okay, what I'm telling you is that, okay, so if you connect a load to this transmission line, actually no need to connect the trans load, okay. If you can consider any point, there is a forward voltage and a backward voltage, okay. So reflection coefficients can be uh, defined as V reflected and V forwarded at any point, okay. So that is reflection coefficients, okay. For example, if you consider this Z is equal to 0 point, okay, Z equal to 0 point, let's say that it is tau 0, okay, so that is equal to forward reflected signal at Z0 is V naught minus, okay, and reflected signal divided by forward signal is V naught plus, okay. So at the load point or Z equal to 0, the reflection coefficients can be written like this, okay. So generally it can be written, okay, it can be written, okay. For example, if you consider any point, okay, let's say that this transmission line is going through, okay, it is not connected to a load, okay. So if you consider any point, okay, any point, yes, tau is normally less than 1, okay. And don't forget that this tau is a complex value, not a real. It can be a real value, but most probably it will be a complex value because these voltages are also can be complex, okay. Mhm. Okay, so it is not a real value, it is a complex value. If you consider the magnitude of this tau, it is definitely less than 1, okay. If you consider the magnitude of this tau, it is definitely less than 1, okay. This tau can be complex also, okay. This tau also can be complex, okay. Okay, if you get the magnitude, definitely, okay. Very clear. For every passive network, okay. For any passive network, this will be true. Okay, but the active most probably active and passive will be true. So you know that the the forward voltage will be this one, V naught plus, sorry, yeah, forward voltage is this one, V naught plus e to the power minus j beta z dou L. Backward voltage is this one, minus e to the power plus j beta z. Okay, so you can write it as V naught minus, because reflected one, to the power plus j beta z divided by V naught plus e to the power minus j beta z. Okay, so you can write it as V naught minus V naught plus e to the power 2 j beta z, because this j beta z is going up and it will be plus. So 2 power will be added. Okay, j beta L or j beta z. Okay, so this is the general reflection coefficients. Okay, so you should understand this equation also. Say that this is 3. Okay, so 1, 2, 3 we have learned. Then we have learned that very important equation, that is um, transmission line impedance equation. Transmission line impedance equation. Okay, impedance equation. Okay, and if this transmission line is connected to the load, okay, so when you are coming, when you are going out of the loads, okay, in this direction, the transmission line input impedance will be changed. Okay, so any input impedance at generally they have in equation we have considered that generally generally for the generally from L distance, okay, from L distance, okay, L distance, don't forget that this L is the minus of is a direction. Okay, this L is minus of is a direction. This way. You can see that uh, here V naught, this should be e to the power minus j beta L now, if you consider is direction. So this is minus plus, no? Here in minus in what the reflected portion, it should be plus, okay? But we have considered minus L direction, so it will be minus j beta, okay? So we can derive the equation for any input impedance at some point, okay? Okay. So it is, we can derive it as Z naught into ZL plus Z naught and beta L, Z naught plus ZL and beta L. Okay. So this is also very important. Okay. Let's consider this a transmission line. Yes, you can plot the curve is at in versus L using MATLAB. Okay, so just try to plot it using MATLAB. Actually, no, normally we are not considering this kind of curve. Okay, normally we use Smith chart to calculate these kind of. Actually, this is a calculation of this is is very important. Okay, you will understand it later. Okay, when we comes to the matching part. Okay. When we come to the matching part, you can understand that this calculating this is a dim is very important, but we are not using any curves. Okay, we are not using any curves. You can see that it is not a linear one. No? We have this is a in has a relationship with L with the L. No, okay, is a dim is related with L. Is a dim is a function of L actually. It is a function of uh, the length. Okay. So there we can plot the curve, but no, there is no any standard curve. Okay. Okay. So let's say that this point is at this equal to 0. Okay. Now a load is connected to the transmission line. Okay. Let's say that this curve, this load is 30 plus J 80 impedance. Okay. This is the load impedance. Okay. This is the load impedance. Now you are calculating. Okay. Let's say that this transmission line length is 0.4 lambda. Okay. 0.4 lambda. Okay. I forgot there is one equation also we have definition we have learned, that is beta. Beta is equal to 2 pi divided by lambda. No. Okay. So this is beta. This is also important. You need to keep remember. Okay. So all these equation maybe you have to use. Okay. So this is the length of the transmission line, 0.4 lambda. Okay. So you are asked to calculate the input impedance of the transmission line here. Then you are asked to calculate the reflection coefficients here, tau, tau C. Okay. So basically you are asked to calculate Z in and the reflection coefficients at this point. Okay. So can you just try to calculate these two things by yourself? Okay. I will give you around maybe 10 minutes. Okay. So try to calculate. Okay, we will try to do. I think you can calculate Z in very easily. Okay, I can't remember the exact equation. I will put it here. Z L plus G. Sorry, J Z not tan beta L. Z not plus J Z. Okay, here I will write the J part. So here J should be there. Okay, J is the compensation. Okay, so now, so I think you know what is this J part, no? What is this? What component made this complex resistance? Yeah, that is so. What kind of what are the components normally this generated? No, no, I'm asking. Normally, you know that if you consider resistor, the resistance is 20 ohm. Okay, so if you consider the resistor, yes, okay. So if you consider resistor, yes, capacitance and okay. So what is this? If there is a plus, it should be a capacity inductance, no? That means uh, resistor connected serially with the inductor. Okay, this is a capacitor connected serially with the inductor. That is 30 plus J80. Okay, so this will be 30, and the reactance actually that is called inductive reactance. Okay, inductive reactance. Okay, inductive reactance, that is 80. Okay, so it is imaginary. Okay, so imaginary resistance normally referred as reactance. Okay, so this is called inductive reactance. Okay, if it is a capacitor, the reactance of the capacitor is minus J C omega. Okay,